Okay, so we're going to start 11.11, which is um, just a little bit more on Taylor, we'll call it Taylor approximations. And all it is using a Taylor polynomial um, to approximate the value of a function. So let's just directly go to an example here. So let f of x be e to the x. And let's say we want to do two things. We want to approximate, we want to approximate the value of e to the 0.1. And what we're going to do is we're going to do it using a third order Taylor approximation, third order Taylor polynomial, i.e. T3 of x, where our center point is 0. And usually when you approximate the value of something using a Taylor polynomial, you're going to want the center point to be close to this x value. So here, the x value that we're going to plug in is going to be 0.1. And our T3, well, is just up to the third order term in our series. So the full Taylor series of f is x to the n over n factorial. We derived that some time ago. So our T3 here is just up to the third degree term. Oops. Should be 2 factorial here and 3 factorial. So this is T3. And all we do now is to get the approximation, we plug in 0.1 as x, and then we use a calculator here to get its exact value. And if you compute it out, you'll get 1.10516666. And there's lots of sixes. Eventually they just put a 7 here because it's an infinite decimal expansion. Now the question is, how accurate is this? So the second question is, how accurate is this estimation? Now, for the purpose of for your final or for a written exam, I'm not going to ask you about accuracy. I'll probably just leave you to go up to here because I'm going to have you guys not use a calculator. I would just say write down the expression that approximates e to the 0.1 using a third order Taylor polynomial. And then you would just write this and you wouldn't even have to simplify it. But at least for the homework, I have 1 or 2 questions where I want you to at least have done it at some point in your life to do the error approximation, the error estimation. And the error, so my procedure is actually a little bit different than the books because I gave you a better version of the Taylor's theorem. So recall that the remainder theorem, so Rn of x, so in this case, the remainder for the third order Taylor approximation, what is it? It depends on the next derivative, the fourth order term. So the next term here would have been, so there's a term here, which would have been the fourth order term. And recall that the remainder is actually the fourth derivative of f at some value c times x minus 0 to the fourth over 4 factorial, where in this case the x that we plugged in is 0.1, and c is somewhere between 0, the center value, this is a, and x, which is 0.1. And that's always the case that, so let me just put everything in absolute value because we want everything in absolute value. This was Taylor's theorem. Again, I stated it a bit differently. It's a stronger result than what is stated in the book. I thought I'll give you the better version. So what do we have to do here? Well, we want to see how big, this is the remainder, this is your error. We want to see we want to get a maximum limit on how big this can be. So for example, first of all, the fourth derivative of f is still e to the x. So the fourth derivative at c, at c is e to the c. Now, how large can that be? Well, e to the c is increasing, or e to the x is increasing. So the maximum value of this term, well, the maximum value would occur exactly at the maximum potential value of c, which is 0.1. This is e to the 0.1 times, so this is what we used earlier was our m value. And so this is m, and then, well, x to the fourth, in this case, is equal to, since it's x is 0.1, we have 0.1 to the fourth, which is 3 zeros here, and 1. And then there's 4 factorial, which is 24. So our remainder overall is less than or equal to the bound for this, we'll just call it m for now, and then 0.1 to the fourth divided by 4 factorial, and this, where m is equal to that, it turns out to be 0.000046, okay, approximately. So this is the maximum error. This is the max error. Okay, so that's the kind of problem you might see in this section. Let me leave you here with an exercise. Now in the book they have a alternating series maximum error approximation. I'm not going to really emphasize that. The more commonly used one is this one. But so let's just leave you with an exercise here. So suppose f of x is the cube root of x, and we want to approximate say the cube root of 0.1 again, and we're going to use, say, a second order Taylor approximation centered at, well, sorry, let me change this actually. Instead of 0.1, let's make this 1.1. And use T2 of x centered at a equals 1. And so that's going to be your part 1 here. Part 2, what is the maximum error. And the, I guess, is a kind of a little bit vague because depending on which method you use, you'll get a slightly different maximum error. But let's go ahead and use my method here. What is the maximum error of this approximation? Okay, I'll leave you with that, and I'll probably do another video continuation of this actually, just to do this particular exercise. And that'll be the end of chapter 11 entirely. So till next time.